Okay. It smells really good. No. I worked at a coffee shop when I was in high school, and we sold like chai lattes and stuff. Well, I don't drink coffee, so that's slightly problematic to this whole game plan. Um, but my ex-husband liked the lattes that I made, so maybe question mark. I suppose. Okay. Yeah, we'll just say yes, and we'll go with that. Yeah, well, I they're just lame. That's all I got. I'm sorry. Uh, out. Blessing is here. Jordan. Steve is not here. He's excused. Lexi, Pharaoh, Largo, Kalasia. Clinton. No Rashaya this morning. Peyton's here. No Layla this morning. Yeah. John, Armand, Hendrik, Jocelyn, Gareth. No Abby yet. Shemaya, no Kaylee. Oh, y'all are like really here this morning. And by that I mean not. There's a lot of y'all absent. Okay, if I have not already handed you your quiz, at some point I'm going to say, hey, we're going to take a second and you're going to work on this. During that time, I will hand back your quiz. I also have like 8 of you who need to make up that quiz. So if that applies to you, please, for the love of God, email me and tell me when you're going to make it up. Otherwise, I'm going to say you don't get to. Okay, so all right, if you just walked in and you didn't see my note to go get one of the worksheets off the back table, please do it. Okay, so we have talked about simple gas laws, which are the gas laws that kind of refer to like before and after situations. You'll hopefully remember from Tuesday that we talked about like first we have this gas at this temperature and this pressure, and then we change the pressure to this, and now what's our temperature, right? That's kind of a before and after. The ideal gas law and the law of partial pressures, which is built into this worksheet but not listed separately, both of those are kind of describing a gas as it is in this situation. So it's not a before and after, it's just here are the things we do know, figure out the rest, right? So hopefully you watched the gas law videos. Sorry if that was loud. Hopefully you watched the gas law videos that I assigned. And if you hadn't watched them before Tuesday, hopefully you've gone back by now and watched them. But talked about the simple gas laws. These are the ones that we were working on Tuesday. They have names. I do not care if you know the names of them. I just need you to know what to do with the formula if you have it. So, yeah. So our ideal gas law. Oh, I should have worn my shirt today. I have a shirt that's the ideal gas law on it. I'm a nerd. It's fine. Anyway, so the ideal gas law allows us to look at some of these things and figure out others with pressure, volume, number of moles, and temperature. All 4 of those things about a gas in one formula. And we can do that because we have the universal gas constant. I think on your reference sheet, I have 0.0821, maybe. I may have rounded it. This number, there are actually 3 numbers for the universal gas constant. and you have to match whatever pressure units you have. So if I'm given pressure in atmospheres, I'm going to use this number. These are the things that are in the box on the front of your reference packet, by the way. There is a box with the three gas constants. Right? So rule number 1. Match pressure units. And hopefully this is something that I don't need to tell you because we've had to match units for other things before. So like if we were talking about liters, we'd have to convert it because we were given milliliters, for example, right? We have to match our units. Pick up a worksheet from the back. So hopefully it goes without saying to match your units. In this case, it's a little bit different because these numbers are very, very different from each other, right? But if I know 3 of these things, pressure, volume, number of moles, or temperature, then I can figure out the 4th thing. All right. We're going to do some practice. I also need to talk to you about Dalton's law of partial pressures, which I have also given to you on your reference sheet. And in my opinion, this is a very straightforward common sense law because what it says is the pressure, the total pressure of all of your gas is equal to the partial pressures of all of the gases that make up that gas, right? So air pressure right now is about 1 atmosphere. What kind of gases do we have in the atmosphere? Nitrogen, okay. What else? I heard oxygen. It's not carbon, but we got carbon dioxide. Oh, time out. Time out. I wrote N. Dumb. It's fine. Right? So what it's saying is that 1 atmosphere comes from the pressure contributed by our nitrogen, the pressure contributed by our oxygen, the pressure contributed by our CO2, et cetera, et cetera, et cetera. And that pressure is based strictly off of what percentage of the gas makes up that gas. Again, we're going to do practice problems with that here in a minute. So we have the ideal gas law where if I know 3 things about a gas, I can figure out the 4th thing. And then Dalton's law of partial pressures. If I know my total pressure, then I have ways of figuring out the partial pressures of each. Grab that worksheet off the back table. All right. Also, and this is important, when we get to lab 14, so I think that's next week for Thursday, Friday. Next week, question mark? Anyway, when we get to lab 14, we'll be using partial pressure or water vapor pressure a lot in that lab. But specifically, anything that's sitting over water, we have to consider water vapor as one of those partial pressures. So let's talk about what this looks like in a question. All right, so under we do. Says a basketball left outside in winter, or is left outside in winter when the temperature is negative 2 degrees Celsius. It has a volume of 6.88 liters, and the pressure inside the basketball is 0.795 atmospheres. How many moles of gas are in a basketball, and what is the partial pressure of oxygen in the basketball? All right, so I am given temperature, volume, and pressure. Remember, if I know 3 things, I can find the 4th. So I'm going to use my ideal gas equation. My suggestion to you, because I want you to always write your units, is to go ahead and rearrange the equation before you ever actually plug in any numbers, because that's a lot of writing if you don't. Ooh, this chair is too tall. Whee. Okay. Don't laugh at me. I must find joy in my life. Leave me alone. All right. So I am asked how many moles. So what variable am I solving for here? Why did it not? Sir. Oh, goody. Why does this hate me? There we go. Okay. Try this again. What variable am I solving for? Say it again. Moles, which is n. Solving for that guy, right? So how do I get n by itself? Divide, yeah. So I'm going to divide by RT on both sides. That'll cancel. So the formula as I'm working with it is n equals PV over RT. And so we can just plug it in. So I've got 0.795 atmospheres, PV, 6.88 liters. Look, I'm literally sitting here thinking through this when I have my answer key right in front of me. Like, what do I write down? Don't know. Look at your answer key. R is 0.0. I'm going to use the number that I wrote or that we're given in this worksheet, which is not rounded. Liters times atmospheres over moles times Kelvin is the unit for that R constant. What? The universal gas constant. It's the thing that allows us to calculate all the other things. We're on we do. And then temperature, which remember our temperature always has to be in Kelvin, so we have to add 273. So -2 plus 273 is 271. All right, my atmospheres cancel, my liters cancel, my Kelvin cancel. I'm left with moles. So I get 0.246 moles of gas. So I figure out what 3 things I do know. I grab my R value based on matching the pressure units. And then I just plug it into the equation and solve. Yeah? Everybody know? What part's sticking? The part where I did the math? Which part of the math? Are we stuck with this? The whole thing. Okay, so this is my gas constant. It was given on the front page. It's on your reference packet. We used this gas constant because you have 3 options. We use this gas constant. Oh no, I didn't round it on here. Yay me. We use this gas constant because my pressure is in atmospheres. Otherwise, it won't cancel. Because you'll notice this one has millimeters of mercury as the pressure unit. This one has kilopascals. So based on whatever pressure unit I have, pick that R value. They're all identical, just with different pressures. Okay. And then this, I had a temperature of -2 degrees Celsius, but then I have to add 273 because it has to be Kelvin. So that's where that number comes from. Okay. Any other questions on the math so far? Okay. So that's how we apply the ideal gas law. All right. The second part of the question is, what is the partial pressure of oxygen in the basketball? Right? So we know that the total pressure is 0.795 atmospheres. We were told that in the question, right? And if you recall from, if I scroll up just a little bit, you recall, this number is equal to the pressure of all of my gases that are in that mixture together. So in this case, I have 3 gases in that basketball. I've got nitrogen, I've got oxygen, oxygen and argon. I mushed them together. I have nitrogen, oxygen, and argon. Okay. So that total pressure is equal to the pressure of nitrogen plus the pressure of oxygen plus the pressure of argon. All right. What do you think it means when it gives me my mole fraction? Part of, yeah, you can say it that way. This is the decimal version of a percent. So it's the percent of my total gas that each gas makes up. So my nitrogen is 0.780 or 78% of my gas. My oxygen is 0.209 or 20.9% of my total gas, right? So the question is, what is the partial pressure of oxygen? Well, I know what percent of the gas it is. That is also what percent of the pressure that makes up. Don't have to do anything times 100. It's just, I've got 0.795 atmospheres. 0.209 of that comes from oxygen. So 0.166 atmospheres of my nearly 0.8 atmospheres of pressure comes from the oxygen that's in the basketball. If it made up 50% of the gas, then it would be 50% of the pressure. If it made up 99.9% of the gas, then it would be 99.9% of the pressure. Does that make sense? Oh, tried to scroll up a little and it just kept on going. We're going to do more with that, so don't panic. All right, are we all done writing this? Okay. The next question is another partial pressure one. All right. A gas mixture at 20 degrees Celsius and 2 atmospheres contains 0.4 moles of hydrogen, 0.15 moles of oxygen, and 0.5 moles of nitrogen. Assuming ideal behavior, what is the partial pressure of hydrogen gas in the mixture? All right. What do I know about hydrogen and the gas mixture right now? And I know moles of hydrogen. So moles of hydrogen is 0.40. Right? That number by itself is not super helpful. However, what can I figure out if I know the number of moles of each of my components? I can figure out the total number of moles, and then I can figure out I could do that, but that's not what I need. You're right, I could, but not where I'm going with this. What did we use in the last question? I can figure out my mole fraction, right? Because my mole fraction is just the thing of interest divided by my total, just like when we're calculating percentages, right? So my hydrogen is 0.4 moles. My total is 0.4 moles of hydrogen plus 0.15 moles of oxygen plus 0.5 moles of nitrogen. So this is my total number of moles. Up on top is my moles of hydrogen. The answer to this is my mole fraction, which is 0.42. Let me add that. There we go.
Are you saying the 0.40 is the total or the whole bottom row?
The whole bottom row is the total. Sorry. The whole bottom row is my total number of moles. I've got 3 gases. I add the number of moles of all the gases together. That gives me my total number of moles present. And then I divide to get my mole fraction. Literally, it's just calculating percentage, like what percent of the total is this, without doing the whole multiply by 100 at the end. 0.4 plus 0.15 plus 0.5. I'm going to be real mad if I have used this answer every single time I have taught this and nobody has pointed out that I mathed wrong. Because now that I'm looking at it, yeah, it's going to be less than 0.4. Yo, that makes me so mad. What is it? Great, we're just going to go with 0.38. Sorry, y'all. Apparently I can't type and nobody catches me, so. You're totally right. I'm sitting here looking at it going, yeah, Okay, well, anyway, oops. Nice catch. I've literally used this exact same math 4 times now, and nobody has caught that until now. Actually, longer than that, because I used the same worksheet when I taught AP chemistry. So that's at least 2 more years on top of that. Makes me so mad. Okay, all right. So now that I know my mole fraction, the question is, what is the partial pressure of hydrogen? I'm just going to do this thing again, where I took my total number of, or my total pressure times my mole fraction. So my pressure was 2 atmospheres times 0.38, and I don't have the answer since I mathed wrong the first time. So that's 0.76 atmospheres. I could mental math that one. No. Okay, time out. I saw a thing that this morning where somebody was reading the comment section of, it was a post about like, you're on the Titanic while it's sinking, but make it Gen Z. And one of the things was like, you know, to the sailor man, how many people can fit on this lifeboat? 67. 67. And I was like, that is very much making it Gen Z. Anyway, it made me laugh a lot. Another one's like, not me dying on vacation. Fair. All right. So again, for the Dalton's law of partial pressures, we've got a couple of things. Actually, let me just do this. Phew. All right. So Dalton's law of partial pressures. That's not a P, that's a D. There we go. So I'm just summarizing here. Feel free to write it down, but this is me just summarizing. So number 1, we can figure out our total number of moles by adding together our moles. just like we did there. We know hydrogen, oxygen, nitrogen. I can figure out my total number of moles by just adding those together, right? This is very simple math, right? I can figure out the mole fraction of any of my component gases by doing the number of moles of that guy divided by the total number of moles in the mixture. I can use the mole fraction to figure out partial pressure. That's not a partial. I can't write today. I can use my mole fraction to figure out partial pressure by just doing my mole fraction times my total pressure. And I can figure out my total pressure by adding the partial pressure of each of the gases in the mixture together. So on that last question, we figured out the partial pressure of hydrogen. If I did the same thing for oxygen and for nitrogen, and then I added all those partial pressures together, that should give me my 2 atmospheres of total pressure. And I hope this, it really is common sense, right? Like, as a group, if we have $100, right, and Josiah's rich, so he gives us 80% of that $100, and I'm super poor and I contribute 1% of that $100, and all of this, like, I can figure out how much each person contributes if I know the mole fraction. And if I add all the parts together, I should get my total, which was that $100, right? It's the same as any other, thinking about a group and doing sort of statistics about those groups. So hopefully this part feels okay, because it's also very similar to a lot of things that we've been doing. We also have specific applications of Dalton's law of partial pressures, which is what we're going to move on to question number 2. All right, so 193 milliliters of oxygen was collected over water on a day when the atmospheric pressure was 762.0. Words are hard. I don't know why. Millimeters of mercury. Pay very close attention to this. You will be doing this in lab 14. So whoever has lab, be ready to do this in lab, please. So the temperature of the water was 23 degrees. Now here it tells me what the vapor pressure of water is at that temperature. You're not always going to be given it in the problem. In lab, you're going to have to measure the temperature of your water and then go, oh, okay, and look it up in a table. You should be able to do this. If I give you a reference table, you should know what to do with it. So in this case, the temperature was 23 degrees. So at 23 degrees, that's our partial pressure of water, which we call the vapor pressure. Okay. So anytime you collect a gas over water, you have to assume that there is water vapor in there and do this piece of math, right? Part A, what is the partial pressure of the oxygen gas collected, right? Remember, my total pressure is equal to the components added together. In this case, I collected oxygen, and I have to just assume that there's water there because I collected it over water. So my total pressure is 762. No, that's right. I don't know the pressure of my oxygen, but what I do know is the vapor pressure of my water. So how do I solve for the pressure of my oxygen? On both sides. So the pressure of my oxygen is 740.9. All right. Once you figure that out, moving forward, this is the number that you use for your ideal gas law. This is where I see the most problems with this math is people will go back and use this number again. No, that number is not your oxygen. That number is your oxygen that is slightly contaminated with your water vapor, right? So don't come back and use this. Use this. Okay. So I now know my volume, my pressure, and my temperature. So how do I figure out how many moles? PivNert. Yes, I call it PivNert. So, all right, I'm solving for moles. So I need to isolate N. So I'm going to do N equals PV over RT. And all I did was divided by that. And that part cancels. So I erased it because I can. Okay. What is the pressure of my oxygen? Right, it's the 740.9. What is the volume? Okay, has to be liters. Yes. All right, and the reason it has to be liters, if we recall, liters is the unit that's in our ideal gas constant. So in order for it to cancel, got to have it in liters. All right. What R value will we use? What R value will we use? Grab a worksheet. Why did you pick that number? Remember to always match your pressure units. I'm not asking you to memorize the numbers. I'm asking you to memorize the fact that I have to match my pressure units. So because it is millimeters of mercury, I got to use 62.36 liters times millimeters of mercury. Your reference packet right here. They're in that box on the front page. And I have accounted for all pressure units that you will see. So again, pick the one that matches pressure units. And then our temperature, what was our temperature? Yes, it was 23 degrees, Kalasia. And then Jocelyn pointed out that it has to be Kelvin, so we add 273. So that's going to be 296. So my millimeters of mercury will cancel, my liters will cancel, my Kelvin will cancel. I'm left with moles. If I wasn't in liters, it wouldn't cancel. If I'm not in Kelvin, it won't cancel. Got to match all the units. That's why we convert. So I get 0.00775 moles of oxygen. How do I answer question C? Someone I've not heard from. Further back. I'm hearing a lot from like the front half of the room. How do I figure out the answer to part C? I need my molar mass. Yeah. This is just stoichiometry conversion type things that we've been doing. As you said, I need my molar mass, which is 31.998 per mole. So that's 0.248 grams of oxygen. Oh, no wonder that was so thick. I had 2 copies. Why did I have 2 copies? Did I screw up the math on both copies? No, I did not. I did the math right on my second copy. Ugh, annoying. I'm ready. Hit me with it. Which one? That guy? That is my molar mass. Yeah. What other questions do we have here? Hopefully I did that math right. Lord have mercy. What? Yes. Okay. Next. All right. This is another type of question. This is if the gas is unknown, we can try to figure it out. I am also giving you the formula for this. It's all right. So the question here is, what is the molar mass of the gas? The way we figure this out is using the ideal gas law that has been substituted. I'm not asking you to do the substitution. I'm asking you to use a formula. All right, we have how many grams, volume, temperature, and pressure. The question is, what is the molar mass? So if you look on your reference packet, right here, it says molar mass equals. Very easy to answer this question if you just plug it in. All right, so molar mass equals the density in grams per liter. How can I figure that out with the information that I've been given? Yeah, when I say density is grams per liter, that per is telling you what math to do. So grams per liter is grams divided by liters. I'm given grams, I'm given liters. So my density is equal to 1.28 grams divided by 0.5 liters, which I apparently did not actually do that math out. I just put it in my equation. So 1.28 grams divided by 0.5 liters. Yay. All right, the next piece, I multiply it by R. Our pressure is given to us in atmospheres. So I'm going to use that one. Times temperature, which I didn't math that one ahead of time either. It's 127 degrees Celsius. Got to add 273 to make it Kelvin. Divided by my pressure. I got 42.01 grams per mole. That's the unit for your gas constant. No, that's the unit. That's the same as me being like meters. We don't do anything with meters. It just is because that's the unit, right? This is just the unit. It's just a very complicated unit because I have 4 things that help me determine that number. Okay. Everybody good on that? Okay. Let's skip down to number 5. All right. Air at 30,000 feet is at a temperature of negative 35 degrees Celsius. A sample of air was collected, and the mixture is 75.56% nitrogen, 23.15% oxygen, and 1.29% argon percent by mass. If 0.594 moles of air are captured in a 45-liter container from a plane flying at 30,000 feet, calculate the total pressure in the container. What formula am I going to use to do that? It is not. Why is it not the partial pressures? It's not that one. That's the question I just asked. Why not? Why is it not that one? Because what? We don't have the total. We also don't have individual pressures. I know what percentage of the gas is oxygen, but I don't know what pressure is oxygen. So because I don't have individual pressures, I can't use that. Yeah. So we're going to use PivNert. Yeah, see, PivNert. we're going to use PivNert. Figure that one out. Okay. Then what piece of information could I use to answer part B? Calculate the calculate the partial pressures of each gas. Yeah, we're going to use our percents to calculate that one. I want you guys to try this one on your own. I'm going to give you 5 minutes to answer those 2 parts. Don't you what? Are you talking about for PivNert? Oh, you would be multiplying. Claysia, what you got? Not in this situation because I'm not trying to find N. I'm trying to find my total pressure. So I'm trying to isolate P instead of N. So close. So I want to get P by itself. I don't want to get rid of P. I want to keep P and keep it by itself. What math am I currently doing? I'm currently multiplying, so how do I undo that? How do I undo multiplication? I'm going to divide by the thing I'm trying to get rid of, not the thing I'm trying to keep. You said divide by P. I don't want to get rid of P. I want to keep P. I want to get rid of D. Because I want P to be by itself.
What's N?
So,
Number of volts.
Yeah, that's a good question.
part B will be
of each of the gases. It's
Number of-
not an exact formula, it's one of the things that I wrote in my notes. You are given moles in this question.
It's the.
It's going to be similar to what we did. Match your pressure units. So in this case, pressure isn't, no. That's true. Great question. You get to pick.
Perfect.
The most common one to use is atmospheres. So I would say go to atmospheres. However, I won't be marking it wrong if you choose differently.
Does it matter?
Huh?
Like, we'll get the same answer?
No.
No, the answer will not be the same. However, the answers will be equivalent. Because remember, 1 atmosphere is 760 millimeters mercury. So it's definitely not going to be the same number, but it'll be the same thing. Does that make sense? It's like if I had a gallon of water or almost 4 liters of water. It's the same amount of water. It's just different. It's 1 versus almost 2, right? Yeah. Okay.
Oh, yeah.
Hey, we're working on question number 2. Yeah. Yeah, so ideal gas law. Pressure, volume, moles, temperature, R is our gas constant, which is your front breath pattern. They're given to you in a tank.
And you said we can use anything for art.
To make sure that because I'm reporting pressure, I give the right estimate based on the R. Yeah, I would personally go with the one for atmosphere, because that's the one that we're gonna use for the but you don't have to use. On a quiz or test, I will specify what is the pressure in atmosphere, what is the pressure in millimeters of mercury, or whatever, to help you figure out which one to use. Let's see.
Thank you. Woohoo.
Hey. Really?
Oh, no, I didn't.
So in this case, it's asking for pressure. You know, when you're doing the other, when you're solving for literally anything else, you will be given pressure and you want to match your pressure units. In this case, I'm not given a pressure, I'm trying to find it, so pick one. And just make sure you report the pressure in whatever unit it
Search try to do it by this by tapping so it's
Okay, so, fun time, that 5-minute timer is up. Any more time? How about another 3? Great, 3 minutes. So,
yeah, that's the
so in the denominator, we have one that's got a denominator and one that's not. And then that's the one reason that our moles is our unit, because what it actually is we're dividing by a fraction. So we put a fraction of moles into the top in our answer. That's fun. Anyway, yeah, you can, yeah.
Oh, I haven't done this part yet. I got, 0.258.
And you roll one.
Value.
Figure out parts of
I said volume. It's volume. I thought he said value. What is the only, if there is a leader on that page, then what number is that?
So the volume of
The volume equals leader, so whatever. Volume always what leader is. So the simulator, you have to make it into leader. Otherwise, volume always so like, in the other question, your pressure's too much, it will not pressure off of that. Thank you. Where does the
Go from.
Yeah, so this is
All
hilariously unnecessary. All things
Yeah,
considered.
minus
I'm pretty sure we take that. And we take these and we,
Ow, sorry. Ashley, Courtney, Jacob, Haley. Okay.
so we turn these into decimals. Zero, 7, 4, 5, 6 times. 0.5.
And for B, we add all the percentages up.
Nope.
We take the percentage of.
My timer's up, so I'm going to go over the answer. All right, time's up. Let's talk about part A. In this case, I'm asked, what is the total pressure? So I'm going to solve for P. That'll cancel out. So P equals nRT over V, right? So number of moles is 0.594. R, I picked the one for atmospheres. It's a longer number, but atmospheres is what we're going to use the most often. So that's what I went with. Temperature, it was negative 35. I have to add 273 to it. Divided by 45 liters. So when I do this, I get 0.258 atmospheres. Right? I swear to God, if you write 500 decimal places, I'm going to have a problem with it. So round it somewhere. Give me at least a couple of decimals. 4 is fine. 4 is fine. Just don't give me 100 and don't give me 1 decimal place. Somewhere in between. All right, so to figure out the partial pressure of each gas, as we said previously, we're going to use our percentages. So if 75.56% of the gas is nitrogen, then 75.56% of the pressure comes from nitrogen. So the only way this is different than question, let's see, we did this under the we do, and we did this for the you do question number 1. The only difference is this was given to us as a percent instead of a mole fraction, which is just the decimal version of a percent. So we have to convert them to decimals first before we can multiply them. But for nitrogen, it's our 0.258 atmospheres times that 75.56% as a decimal. So 0.195 atmospheres for nitrogen. And then I'm going to do the same thing for my other 2 gases. For oxygen, it's that same total pressure. times the partial pressure of oxygen as a decimal. And then I'll do it again for argon. And if I add all three of those up, that is a really ugly 3, sorry. If I add all three of those up, I should get 0.258, or just about, depending on rounding. Okay, this next question is kind of merging the stuff from chapter 4 with the stuff that we've been doing in chapter 5. So, how many grams of potassium chlorate, KClO3, were reacted if 5.30 liters of oxygen were produced at 117 degrees Celsius and 0.995 atmospheres? Given the information that we have, what formula can I use and what can I find with it? If I have atmospheres, liters, and degrees Celsius, I can Pivnert, yeah. And what do I find if I plug those in? I get moles. Given a balanced chemical equation, can I find grams of something? I can, because stoichiometry. That's all that stuff from last chapter. So this is kind of bringing it all together, right? So first thing I'm going to do is figure out my number of moles, and then I'm going to have to do stoichiometry to figure out the answer. So N is my number of moles. So PV over RT. Got 0.995 atmospheres. 5.30 liters. Which R value do I use? Why? Yeah. Again, remember, we pick the R value by matching our pressure unit. And then our temperature was whatever 117 plus 273 is. Thanks. Good call. 390. Where is, I swear I just heard my phone vibrate, but I thought my phone was up here. Oh well. Anyway, it's fine. All right. So we get 0.165 moles of oxygen. All right, now, what do I do with this in order to answer the question, how many grams of potassium chlorate were reacted? So close. We have to do something else first. Using what? What do we call it? Yeah. The mole ratio, yeah. So I've got moles of oxygen. I don't care about oxygen. My question was about potassium chlorate. So that's where this comes in. And it's Cl. For the love of God, y'all are still doing it. It's Cl. It's never Ci. Literally never. Literally never. And then I go and I grab my 2 and my 3. Now I need my what, Largo? Now I need my molar mass. So 1 mole of KClO3. Molar mass is 122.548. And I get 13.48 grams of KClO3. Okay. Take a look at question number 7. What formula could I use to answer question number 7? Molar mass? More words. Uh-huh. I can use that one. Yeah. Okay. I am not given my molar mass. However, y'all know how to find it. Yeah, I use my periodic table. I can go find the molar mass. I'm just going to have to rearrange this formula that we used earlier. So when it says molar mass equals, just got to rearrange it to find density. Okay, really quickly, I'm going to let you guys do that one, and I'm going to let you, we'll talk through number 9. But number 8, really quick. By what factor will the pressure of a sample of gas change if the volume is reduced by 1/3 while the Kelvin temperature is doubled? Anytime that you are given like non-specific information, like what if I double it? Literally just make up numbers. And my suggestion to you would be to make up easy numbers and then do practice math. So for this one, what happens to the pressure? So P equals nRT over V, right? If my volume is reduced by 1/3 and doubling the temperature. So literally just make up numbers. Again, make it as easy as possible. We'll just say it's 1 mole and we'll start at 1 Kelvin and 1 liter, right? So then we've got 1 mole times R times 1 Kelvin divided by 1 liter, get an answer. And then say, okay, well, what if I reduce my volume by 1/3 and my Kelvin temperature is doubled? So 1 mole, R value. I doubled my Kelvin temperature, so now it's 2. And I reduced my volume by 1/3, which means it's now. I reduced it by 1/3, right? I'm going to go 0.67 because 0.66666666 will round up. So literally just, if you're given some sort of generic question, make up numbers and make the numbers as simple as possible. If I want to know what happens when it doubles, okay, well, it goes from 1 to 2. If you don't like, just make up fake numbers, it's fine. This for part A, and then all 3 of these for part B.
Oh, I thought we had to add them up.
No. Although if you add them up, you should get 0.258. Right, yeah. So that tells you did it right. Because remember, your total is equal to all your parts added together. All right. Number 9, the diagram is not really great. But essentially, what we have is, we have 2 containers of gas. We got this guy that has nitrogen in it at a pressure of 2 atmospheres and it's 2 liters, right? Then we have this container full of oxygen. That's a bad circle. That is at a pressure of 4 atmospheres, and it's 3 liters. So the question is, what happens when this valve is opened? What's the final pressure? When the valve gets opened, what do these gases do? They mix. because gases are moving in constant random motion and will expand to fill whatever their container is. That's the reason that I could break a bottle of perfume over here and Quentin would smell it over there eventually, because the gases that make it smell spread. That's the reason if you walk in the hallway by my office, it smells like a cookie, because I have a wax warmer in my office and the whole end of the hallway smells like a bakery because the gases are expanding and spreading. So when I open that valve, that nitrogen that was just in here is going to expand to also be in here. That oxygen that was in here is also going to expand to be in here. So now both of them occupy a container that is a total of 5 liters. What two things are we looking at in this situation? Pressure and what? Pressure and volume. We have a gas law for that. So we can calculate the before and after for each of them. Like, we can use our before and after situation because nitrogen goes, so for nitrogen, for example, nitrogen goes from a pressure of 2 atmospheres and a volume of 2 liters to some pressure, and now the volume is 5 liters because it has both sides of the container to exist in.
What about the before and atmosphere?
That's oxygen. So we'll do that math different. We'll do that math separately. So for nitrogen, the new pressure is going to be 0.8 atmospheres. And then you'll do the same thing for oxygen because oxygen starts out at 4 atmospheres and 3 liters and ends up at some pressure in those 5 liters. So for oxygen, if you do the same thing, we get 2.4 atmospheres. So the question is, what is the final pressure in the container? How do I figure that out? Yeah, why? Because of Dalton's law of partial pressures. You're right, we do add them together. And that seems common sense, but it also is very much formula based. All right, I've got one more worksheet to give you guys on gas stoichiometry. So this has the answer on the bottom of the page. We're going to get through as much as we can, but we only have about 10 minutes left because if you were in here when I was talking about it, we have a severe weather drill at like 11:03 or something really dumb. Why it can't just be a nice even number, I don't know. But anyway, so we're going to lose like the last 10 minutes of class.
Oh, yeah, sure. We do have class. Hey, Brett.
Yeah, in case you're wondering, it was my game. Because former athlete, so fun. Arthritis literally everywhere. Okay. All right. So we are supposed to use this balanced equation, which is the reaction between gasoline, or the octane in gasoline specifically, and oxygen that happens inside your car engine. So if 4 moles of gasoline are burned, what volume of oxygen is needed if the pressure is 0.953 and the temperature is 35 degrees Celsius? Okay. I am being asked to find the volume of oxygen. What is the first thing I'm going to need to do in order to answer that question? What equation? No? We're not working with density here. I mean, good try, but no. All right. I have pressure and temperature and number of moles. Do I have all of the information I need about oxygen in order to then use a formula to find the answer? Ha, that is a great question. That's because, no, I don't have all of the information that I need in order to figure out about oxygen. So what do I need to do before I can calculate whatever about oxygen? Okay, I need to write what I have to find what? So I need to find my moles of oxygen, because then I can plug it into what equation? Pivner, yes. All right, so I just didn't feel like writing C8H18, so I just wrote gas. But gasoline is C8H18, so 2, and then 25 for my oxygen. So I got 50 moles of oxygen. So just keep in mind that I have to have moles, pressure, temperature, volume. Those things have to all be for the same substance. In this case, y'all asked, ladies in the middle row, why is it volume of gas and then volume of oxygen? You need to be able to recognize, oh, hey, I have a volume, but it's not of the thing that I need. Or I have moles, but it's not of the thing that I need. You have to be able to recognize that, because they have to all be of the same stuff. So now I have, different color, moles of oxygen, temperature, and pressure. I can find volume now because I have all of that for oxygen. What? Oh, okay. I heard you say something, but I didn't hear what, so I was very confused. So now I'm trying to find volume, so I'll divide by my pressure to isolate volume. So that's number of moles. We just calculated that. I'm not going to write oxygen. What R value do I use? Yeah. Temperature was 35 degrees Celsius, so gotta be Kelvin. And then my pressure is 0.953. So just for the record, this is why fossil fuels are such a problem for climate change, because this is for oxygen. 4 moles of gasoline, which is like, I don't know, a couple hundred grams of gasoline, makes 50 moles of oxygen. But it also makes 32 moles of carbon dioxide. And that's a really big volume of carbon dioxide. So for the oxygen here, 1,326 liters of oxygen will be used. That's a whole lot of oxygen. So internal combustion engines are terrible for, life on Earth. Let me see what time we're supposed to be doing whatever.
You want to put 0.05?
Nah. Yeah, I was right. It said 11:03. We got 6 minutes. Okay. So now the next question, how many grams of water would be produced if 20.0 liters of oxygen were burned at a temperature of negative 10 degrees Celsius and a pressure of 1.3 atmospheres? Do I have all of the information that I need to answer this question? What do I need? Okay. In order to get to grams of water, I got to figure out moles of water, right? But what I'm given is lots of things about oxygen. Not yet. So what I can do here is I can PivNert to get to moles of oxygen, and then stoichiometry to get grams of water. So the beauty about the ideal gas law is one component of this is moles. That means that I can take any reaction that involves a gas and do some stoichiometry so that I can talk about the volume and the pressure and the temperature of the gas while also specifically talking about the reaction, because moles is part of our ideal gas equation. All right, so we have 3 minutes until this lovely severe weather thing. So I'm going to let y'all pack up. So what we have to do if we are in this room and get severe weather called, we have to go into that like hallway space by the vending machines. Everybody on campus is doing a severe weather drill. But for us in this room, that is our safe space. So what I want you to do is go ahead and pack up. Take your stuff with you, hang out there until we get the all clear, and then you can go. We have been instructed to make sure you take these things very seriously. So hang out until I say so, and then we'll go from there.